three presenters, so this is going to be a little bit more in-depth presentations. They have a little bit longer to share with us what they're doing. This session is called Creative Design in AR, and we're going to start off with a pretty neat little device, if y'all hadn't had a chance to check out, that Fabrizio Polo is going to be sharing with us. So please, take it away.
Okay, so my name is Fabrizio Polo, and I'm a computer...
Maybe a little bit closer to the mic.
Computer? No, there's no light on it. That's my phone. I turned it off while we were setting up. I apologize. There we go. It's on now. Okay, is that better? Yeah, that sounds better. Okay, so I'm Fabrizio Polo, and I'm a computer vision engineer at Robotics, and I gotta apologize a little bit preemptively because this is actually really a hardcore tech talk and does not deserve to be in the design room, so I hope all of you who appreciate it do, and all of you don't can leave. No, don't leave, don't leave. Okay. So the main point of this talk is to show how you can use things that aren't strictly augmented reality or aren't strictly vision related or aren't strictly tracking related or all these sort of mainstream augmented reality tools to actually enhance augmented reality a lot. And in our case, we're dealing with a robot, okay? And it turns out that the robotics really help you in many ways because they give you a new source of information even when all of these other sources fail. And obviously things like monocular slam or other tracking strategies, they can be kind of flaky even at their best. So Sphero, I don't know who's seen it. This is our product, and it's a robotic ball. You can drive it around. You can connect to it with a smartphone, and we use it as a moving robotic fiducial. It's a marker, and it's got enough information in it, despite being round, to give you not only its location and its orientation, but the location and orientation of a mobile device as well. And if you put all that together, that's enough to make a pretty good augmented reality experience. So Sphero is a robot, and it has a bunch of sensors in it. And it communicates with a mobile device, and that mobile device also has sensors in it. And so, just trying to do the best you can, you end up trying to use every shred of information available, and there's a lot of good stuff you can get out of the sensors. So Sphero itself has a gyroscope, an accelerometer, and a thermometer in it, which turns out to be related. And so the gyroscope gives you angular velocity, so you can tell if you're rotating, and the accelerometer tells you approximately which way is down. This also has wheel encoders, so we can tell inside, as the thing drives, how the wheels are rotating. And so, in a situation of a robotic car, it's pretty easy to convert that into some estimate of your motion, but with a ball, you have to work a little harder because it can be in all sorts of funky orientations. But that also gives you some sort of location information. And finally, you can communicate to your smartphone with Bluetooth. Okay, so on the mobile side, you also have an accelerometer and a gyroscope, usually. And you have a video camera, which is really the big sensor, right? So these sensors are all pretty good, but they don't give you very useful information by themselves. And what you really want to do is take multiple sources of information and either combine them into something that's like greater than the sum of their parts, or somehow filter the original results so that they're more meaningful or more stable or more accurate. The same way like a human being, if I watch a person walk behind a post, I'm not confused that suddenly they've split in half and now they're, oh, now they've arrived whole again. Wow. No, I'm not confused by this because I have a lot of sources of information that I can put together to make a stable representation of reality. And totally vision-driven augmented reality, you can see it suffers from the breaking as soon as there's a lack of information. And so primary example of sensor fusion is, of course, what you get in most smartphones, where you have an accelerometer, which is sort of this constantly pulling, kind of telling you which way is down, and you have a gyroscope that you're using to figure out how you're rotating. And when you put the two together, you get a pretty good concept of orientation. And that's sort of the classic example. But I'm going to show some more examples of how you can fuse sensors together and get really useful stuff out of it. So let's see. What else can you do? So dead reckoning. Dead reckoning is sort of the term they use for figuring out which way you're going or where you are or how you've moved, but with no concrete external reference frame. And that's the key. If you have some sort of outside way of checking yourself, you can, for instance, GPS, right? GPS is pretty good, plus or minus some fixed amount, right? GPS is never going to be 10 miles off. After 2 years, it's never going to get further off. It's plus or minus some approximate constant, and that depends on where you are, but it doesn't just drift. Our IMUs that we have drift horribly. They drift a little bit in terms of their orientation understanding, and that's difficult enough. But in terms of actually knowing where are you based on reading an accelerometer, like, give up. Give up. It's not going to work. There's this awesome video on YouTube where John Carmack talks about how he thought, oh, well, I took calculus, so you just integrate twice. That should work out. And then probably no one told him it wouldn't because he was John Carmack, and he tried it and it didn't work. So that's really hopeless. And if you want some sort of absolute position information, which you really need to generate a good AR experience, you have to work harder. So Sphero has a service running on it where we attempt to integrate up all of the motor movements. We attempt to use the orientation of the robot inside the plastic shell and put all that together to figure out which way it's twisting the shell. And then if it's twisting the shell this way, well, the ball's going the other way. And so if you integrate that up all the time, you get a pretty good understanding of where the ball is, and it gives you a result as 2D position estimates on the floor. And if there's a little slippage or a little error, yeah, you may pick up an inch of incorrectness, but you're stuck with that inch forever. That inch doesn't slowly turn into 5 inches or a yard or something and become useless. And that's the main thing that's different about this type of technique versus just integrating what you get out of an accelerometer, which diverges rapidly from reality. So another example of some sort of sensor fusion we have is we're combining results coming out of the accelerometer and the gyroscope, and we're running it through something we made with a little machine learning that attempts to figure out the difference between what is just the noise from bumping around on the ground and what does it look like when you've hit something. And so it gives good results there too. So when you run into something sort of substantial, then you can tell without any vision. Okay, so I thought this was about AR. It is. Okay. So the other main thing we do is we actually track where the ball is in a video stream. Okay, so this is the main thing you'd think of as augmented reality. So we have our own custom tracking algorithm. The main thing it does is figure out where the ball is in 2 dimensions in the screen and also how big it is. And the size really is the same as the distance when you think about it, right? If you know genuinely how big this ball is and you know how big it appears to be in the screen, then you know how far away it is. And so you'll see what we'll do is combine that with some other sensor information and get a lot more out of the total. So one of the positive things that we get from tracking Sphero is that because it is round, it looks the same from every angle. And you can track it at quite a long distance because you're not looking for subtle features and corners and things like that that make tracking, for instance, a similarly sized paper marker, pretty hard at a long distance. Another positive feature is that because it's a ball, if you blur a ball, you get an ellipse, right? But if you blur a corner, you get nothing. So that's another thing that makes it really convenient for tracking. It makes it a lot more indifferent to just random noise and chaos. Okay, so what do you actually need for AR? I've listed, there's all these sensors that I've kind of rambled about, and I've mentioned that, yes, we also track it, but what do you actually need to get AR done? And the bare minimum is you need a camera orientation matrix and or position, right? That's the very, very least. If you have that, you can draw made-up content. In our case, we'd like to draw some characters too, and I'll show you in a minute the demo app, but we'd like to draw a character over the ball so it appears as if you're driving it around your living room. So for our purposes, we also need to know where is Sphero. Okay, so these are all the things we need. We need to know where is Sphero so we know where to draw it. We need to know what is its orientation so we know how to orient the model. And then on the camera side, we definitely need a camera orientation and we definitely need a camera position because you can't draw anything without that. Okay? So let's go back and go through all the sensors and show where are we getting all these ingredients? What is it that how do you actually put these together to get something? So what do we have? Sphero position. So we have this locator service. It's running entirely on the ball. It's just operating blind. It feels its wheels turning, it knows which way it's facing, and it just adds that up and computes some position. The Sphero orientation, well, there's the IMU in this, so that's how we know which way the physical robot is facing, so we can figure out which way to draw a model on top of it. Camera orientation. Fortunately, this kind of thing is sort of done for you for the most part. It's not perfect, but if you want to rely on just the IMU and not real modern SLAM techniques, then it's sort of done for you by Apple or Google or whoever. Okay, but camera position is a big blank. Right? Like, what are you going to do out of any of that that's going to tell you where you are? And after all, that's the most important thing because that's what it takes to place a virtual camera in a virtual world and then take a picture. So it turns out that you can put all these things together and you can get this result. So, so we need to combine all our previous results. Okay. Now, one thing that may not be so obvious is that there's a sort of issue of coordinate systems. You know, anytime you wake up your iPad, like if I'm facing this way, I turn it on, the iPad says that's 0. Tomorrow I'm facing this way, I turn it on. Strangely enough, it's again 0, right? Doesn't matter what you do, when it wakes up, it's 0. And Sphero has the same, it's not a problem, I mean, it's a feature of the universe, but that's the way it works. So Sphero has the same constraint. Every time it wakes up, whichever way it's facing is its 0. And the problem with a sort of two-component augmented reality system, like you have this phone and you have this ball and they each have their own sensors, is that how are you going to connect those two systems? I wake them up this way, I wake them up that way, and they're uncorrelated. So what you actually do is you need to observe the ball in motion, and if you ask the ball, which way are you driving, and you observe the ball and you know which way it appears to be driving, then you know what the difference is between the coordinate systems, because they're saying this is my 0, I'm saying that's my 0, well, there's 50 degrees between them, and then I just get to use that constant to do the conversion after you've done a little observation and sort of machine learning. And so that's a really key thing that gets these two components together. So basically, the way it ends up working is the ball knows where it is. After a little learning, I know what our orientations are with respect to one another. I know where the ball appears to be, and when you add those together, you figure out where you are, right? So if I say to my friend, where am I? And he says, well, you're a mile east of me, and I know where he is, well, then I know where I am, right? And that's exactly what's going on here. You're putting those two things together to figure out where the camera is, and then that allows you to do the rendering. So this whole talk is about how awesome robotics is, because it makes augmented reality all that much easier. And so I put together a little demo here to show you. I hope it will work here. So let's see. Can we switch to the? Is there something I should do to switch to the iPhone? Oh, maybe I'll.
Is there?
Oh, okay. Okay, sorry, I guess I should have connected to this already. Okay. Okay, so that's not the right one. Okay, so this is our first AR app we made, and last Thursday I made a sort of hacked version which does some things a little differently. And the idea was to modify the way it's implemented so that basically when vision quits, it doesn't quit. When vision quits, it just decides, I'm going to do the best I can with the missing data and see what I get out of it. Okay? So let me start this guy here. Started the wrong one. Okay. Okay, so you can see it's tracking the ball and all is well and good. It knows which way it's facing, right? And in fact, the facing, if you notice, the ball's round, so you can't see that the ball has just changed orientation. That's entirely driven by the robotics of it. It knows as a result of the Bluetooth connection and the signals it's getting back, you have rotated. So what I'm going to do is just cover up the camera and we'll see how well the game continues to play without video. And without video, it's a little choppier because I did not optimize it for that. But here we go. Okay, so it was off by about 4 inches going dark. So let's try again. Maybe drive back into the circle here. Okay, another couple inches. So that's AR in the dark. I mean, that's as much of the engine as functions without actually being able to track the object at all. So what happens there would be, as soon as the object leaves the scene, the camera position freezes because it really doesn't have any ability to decide if the camera's moved, and then just says, based on the robotics, what is actually going on. And this is a lot more than a gimmick. I mean, if you're driving through a crowded room and the ball is going behind people's legs, this robotics is exactly the kind of thing that keeps tracking working in the brief seconds when you have other difficulties, or if you just take it out of frame, you know it has not moved. If you take it out of frame and look the opposite direction, you can simply stop looking in vision because you know it's behind you, because the ball has not moved and neither have you. And if nothing else, that probably saves a lot of battery life. So, all right. So in conclusion, robotics really does help a lot. Helps fill in the gaps when tracking breaks down. And it provides invisible information. Like, for instance, if I take the ball slightly out of frame, I'm no longer tracking it, but I can still drive it off frame, right? So you can get a lot of really interesting things out of robotics that you would think are normally the domain of vision, and that really helps AR. So that's it.
Questions? No? Ladies first.
It's very easy. You mentioned a thermometer. What is the purpose of the thermometer?
Oh, yeah, that's a good point. So it turns out that all of these MEMS sensors are actually temperature sensitive, and that the results they produce are dependent on all sorts of weird things you wouldn't think they should be. And so it's actually correcting the accuracy of those sensors. Like, for instance, if you had a really low quality camera that pictures appeared to be tinted sort of red when it was too hot out, right? Like, you could correct for that in software and get more accurate pictures, even though picture taking should have nothing to do with temperature. So that's really where that comes from.
Okay.
So you talked in the beginning about, you know, if you have somebody that moves behind a post and taking all the information and kind of correlating it to get a fusion and know where you're at. It seems like a big piece of that is memory. Can you talk a little bit about whether or not you use historical sensor data from all those different sensors to make it work, how that comes together?
Oh, yeah. Almost everything is tracked in one way or another. And
Speaker, please.
Oh, yeah. So almost all that data I'm talking about is tracked from one frame to another in one way or another. techniques that just sort of take now into account can sort of look good, but they break really quickly. So almost all of that data is tracked. And in fact, some of the stuff where we're doing correlation between where the ball appears to be moving and where the ball thinks it's moving, that's solving mathematical optimization problems that are looking at 40, 50, 60 seconds worth of data as the app runs, because it can get a more accurate result by looking at all the motion over the last minute. So yeah, some of that is a lot of historical data.
And I'm curious, two questions. One, what is the cost of Sphero? And two, is there a discount for attendees of the event?
Okay, there's good answers to both of those questions. It's $129.99 normally, and you can get it at Brookstone or the Apple Store or our website online. And for the conference, we have a $99 special. So if you go to our website and you log in and you use the code, I think AWE99, you can get one direct from us for $100. But do it fast, because I'm not sure when the code expires. So.
Any other questions? Okay. Thank you very much. Appreciate it.